Welcome to Big Idea 4. When we get into kinetics, we're going to look at rate laws and mechanisms. The first thing we need to understand here when we get to rate laws is what exactly a rate is. And we define a rate by, in the most generic terms possible, it's the change in concentration of a reactant over the change in time. So the positive and the negative signs just tell us a direction. Are the reactants and products going up or down? But in general, we just talk about them in positive terms. So if we have a generic reaction here, graphically, if we looked at all of the substances together, we could see how these would overlap on top of one another. And we can start with different concentrations. If we had different molarities and then different times, time 0 is going to be my initial. That's going to be really important, because sometimes you get that in data sets and it's not always clear that that's the very beginning, but that's what you have. And in general, as the reaction progresses here, if we're starting with our reactants and no products, we're going to see our reactants go down with time, and then they start to level off at a certain point. Let's call this one A, and then B is going to go down a little bit more gradually and then taper off B, and then C is going to go up even more dramatically, and they all kind of level off at the same point there. Generically, we'll just call that like our equilibrium point when the slope stops changing and they're all 0. But the way that these change is based off of their coefficients. They're going to change in a 2 to 1 to 3 ratio. For every 2 A's that I lose, I'm going to lose 1 B. So we see our A line is much steeper than the B line, which is a little bit more narrow. And then the C line, I'm going to increase 3 times faster than the others. So we kind of see this generic trend here with the rates. So we want to be able to compare slopes of these as well as coefficients. And this is the most simple question, comparing one molecule to another. Now when we get into rate laws, all of your rate law data is going to be defined for you by one variable. This is all the data with respect to B. And then you get questions that are like, well, what about A? Well, A is going to be twice what B is. So don't get lost in your data. See how your data is defined, which variables it is defined as. We then get into reaction orders. So if we had a generic rate law that said rate, and these are always, we say these are our rate laws, K, A to the something. Let's say K, A, B, and then just to skip around on you here, we'll do D. The reason we would have D is because C maybe is 0 order, so it doesn't appear. So we want to analyze this by saying things like, okay, the overall order of this rate law is going to be fourth. N equals 4, and we say the order is going to be N. N equals 4. We need to get the units of K, and the units are pretty much always related to the overall order. And the units are going to be in the very generic sense. Here we have molarity, molarity, and molarity squared. So that's molarity to the 4th power. We're going to cancel out 3 of those because a rate is defined as, if you remember, we defined it as concentration over time, molarity over time. Well, I have 4 molarities, and I only need 3 of them. So we're going to invert that, and we're going to get liters over moles. That cancels out 1 of the molarities, but I want to cancel out 3 of them. So liters cubed, moles cubed, and then I'm going to say time is always going to go down here. Usually we're in seconds. Watch out, though. Sometimes it's in minutes. And you just get the generic formula here. Whatever your overall order is, you're going to cancel out all but 1 of the units of that. So liters over moles. and then the time is always going to get inserted on the bottom. It could be minutes, could be hours, wherever you are. So we want to be able to predict those. And of course we get this rate law from rate data. We see that as concentration of one thing changes, if it doubles and the rate doubles, it's first order. If the concentration quadruples, or I'm sorry, if the concentration doubles and the rate quadruples, we get a squared order relationship. So we want to be able to derive these rate laws from rate and time data, figure out the order, and then the units of K. And that'll give us, we call those the differential rate laws, or simply we usually just say that is a rate law. The much more difficult ones are going to be the integrated ones. That's where we're going to do a little bit more of our math into the integrated rate laws. So when we get into the integrated rate law, we're going to compare it to the differential rate law, which we often just call the rate law again, for three scenarios with single variable equations. So zero order, we're going to get rate is just equal to K, because K a to the 0 goes away. First order, rate equals K a to the first, and second order rate equals K a squared. That's the standard differential rate law. This measures the data you would see for this is rate versus concentration. See how one changes, how does the other change? The integrated rate law if you go through the calculus, has time put in. So the concentration equals negative kT plus the initial concentration. That's for a zero order rate law. A first order will integrate into a natural log of the concentration at any given time, equals negative kT plus natural log of the initial concentration. And the second order is going to integrate into an inverse relationship 1 over the concentration at a given time, equals positive kT, be careful there, plus 1 over the initial concentration. So when you see concentration versus time data, you know you need to use the integrated rate law. Now, when you get these rate laws, you can go back and forth between them. If you know that it's zero order, you can use both equations. So the problem sets you see for these are pretty similar in terms of what you're asked to do. One, depending on which data set you have, either rate data or concentration time data, you need to find the order. Is it going to be 0, first, or second? The second thing you need to do is usually just write the rate laws. And you can write both of them. And then you can find K. You use some of the data that you have to find K, including units. And we went over units before. Now it's important here to see when you have the integrated rate law data, these are all in the y equals mx plus b format. So K is often your slope, y equals mx plus b. The slope or the negative slope, because here second order it's your slope. First and zero order it's negative kt, so negative k is your slope. All the k values are going to be positive, but you can use those. Sometimes you use graphical data to find k. And then the last thing they do, once you have k, once you have the rate law, you need to apply it to a new situation. So then you can use k, use the rate law to get new things. And remember, sometimes they do these with percentages. You kind of make up your starting amounts. Sometimes they do it with fractions. So let's say, maybe you have 1/8 of something left. Well, you have a starting point, and then you ended with 1/8 of it. So don't get lost with some of those simpler things. And if they do ask you to use your calculator for these, we do want to be able to do that. So our calculators, to make lists, if you needed to graph these, you need to be able to make a list in the Stat Edit button. You need to be able to do a linear regression test. And that's in the, if you hit Stat and then you go over to the Calc tab, you can do a linear regression. And if your diagnostics of your calculator need to be on, which they shouldn't have been unless you reset your calculator, they should always be on, the r-squared value, we want it to be as close to 1 as possible. And then your slope, if depending on your calculator, if that's A or B, k is going to be whatever your slope is. It should just be a positive number, absolute value. So don't forget how to use your calculators in case they ask you how to do that. The last thing we want to do, and I'll put it down here in the corner, is half-lives. Sometimes half-lives come up. Now, if you know how to use these equations, you don't need to memorize any half-life equations at all, because half-life just means your concentration is half of what you started with. So if they give me a starting amount for 0 order, cut it in half and then end with your final concentration. If they give me the time, half-life is a time, so they're usually asking you, okay, how much time does it take to get to 1/2? Or the half-life is 4 hours, how much will be left, or how much did we start with, etc., etc. So you can kind of work through those. It's the same kind of idea. Even if they give you the half-life, you can use that. If you have the time and you know the starting and the initial, you can use that to find k. And then if they gave you like a different amount of time, you could apply it to get new concentrations and new times. So the half-life problems are really just applications of these. The only thing worth mentioning is the half-life that you think of, where it's like, hey, 4 hours, half decays, another 4 hours, half decays, another 4 hours, half decays. That only works for first-order kinetics. And those are the ones where they don't have to give you a starting amount, just the way that natural logs work in that equation. If you can just make up a starting amount. Say you started with 100 and then you ended with 50. You ended with 0.5. All nuclear chemistry is not dependent on what you start with. Any first order rate law problems, the half-life is the generic one that you're kind of familiar with. And we don't really look at the equations for the other ones too much. But they're just applications of these rate laws. So think through them. Know that when they say half-life, they're talking about a time. And you can use those, again, to just find k and apply it to new situations if you know the order. The rest of kinetics will talk about collision theory, mechanisms, and a little bit of graphical analysis. When we get to a mechanism, it's important to note that our overall balanced equations they don't actually tell us how the reaction happens. So if I had an equation that said 2a plus b turns into C and D, that would require 3 things to collide. That word that we said was molecularity. It'd be really rare for all 3 of those things to collide at the same time. We don't know how these are reacting to turn into C and D. We just know that the overall process makes 2 A's and a B turn into C and D. So we get a rate law, and it has to be determined experimentally. We just need data. There's no way to know what the rate law is. Mechanisms, on the other hand, mechanisms are just kind of guesswork. So if we had said, okay, B maybe decomposes into C and E, and then A is going to combine with this E that we made in the first step to make F, and then another A is going to combine with that F to make a D. Well, we need to check two things here, and then we would just kind of randomly say, okay, this one is slow, this one is fast, and this would be given to you, and this one is fast. We check two things. We say, okay, does this proposed guesswork mechanism add up to the balanced equation? And when we cancel out terms, we see that E is an intermediate, we see that F is an intermediate, and we get B, 2 A's makes C and D. So that checks out. The other piece is the slow step. The slow step rate law is different. The slow step rate law, when we get into a mechanism, it is actually the coefficients of the things that collide. B to the first power. So this would be not dependent on A. So how do we know if this mechanism is right? Is because these rate laws need to match. So we just say, do they match? If they match, then this is probably a good mechanism. If not, then it's not. Sometimes you have to do substitution. If you have intermediates or catalysts in your rate law, you need to substitute them out, and that can happen too. So just to differentiate here, to keep going with that intermediate term, when we look at an intermediate, if I could spell, an intermediate is something that is not there at the beginning. We make it in one step, and then we use it in another. A catalyst, on the other hand, is something that we have control over. We add it at the beginning, and then we get it back at the end, and it's never fully consumed. We have as much at the end as we started with. Catalysts, we're going to get into a little bit more detail here, because what they do, they lower activation energy, they provide an alternate path for the reaction to travel on. Sometimes they can help molecules collide with the right orientation. And then in biology, enzymes, it's good to know that those are catalysts. They combine molecules in such a way that it's easier for them to react. And when we look at our potential energy curves, we see, let me change this graph here, get two graphs. If we had our potential energy curve with our activation energy this way, the catalyst is going to give me an alternate pathway with a lower activation energy. So we can see how it affects the activation energy of a graph. If we were to look at this, another type of graph we use are distribution curves with the number of molecules that we were looking at with gas laws. There's an kinetic energy threshold. This is a potential energy curve, the kinetic energy distribution. The activation energies are usually a threshold, and anything past that, these are the molecules that are past it, can react. Well, if we lower the activation energy on this one, it's going to go this way. Lower energy is now on the x-axis, So this is going to allow these molecules to react as well. So catalysts, depending on which kind of graph we can look at, we can analyze these blue ones here. These are the catalysts, the effect they have on the reaction. Which ties us into collision theory. And collision theory is just our reminder that molecules need to actually collide with one another in order to react. So they are bouncing around in space, they collide, they move off one another, and when they collide, not every collision results in a reaction. They need enough energy to get over the activation energy, so there's a minimum energy threshold, and they need to collide the right way. We call that orientation. And again with the spelling. So they need enough energy and they need to collide the right way. And different factors that affect those things were just what affects the collisions. The rate of the reaction is temperature, so we want to be able to discuss these things. Higher temperatures mean faster molecules, more kinetic energy, more collisions. We can look at concentration. If I have more stuff, I'll generally get more collisions. If we had gases, pressures and volumes will affect rates. If they're in less space or more space, and depending on the pressure, we can do that. Catalysts, we've already talked about. Catalysts can improve the orientation and bring molecules together, provide an alternate pathway. And then another one that we did was surface area. If you crush something up, more molecules are exposed, so you can get more collisions. And it's worth looking at these distribution curves again, especially when we're looking at temperatures, because if we had a kinetic energy graph, and this is just kind of number of particles, it's like a bar graph, but it's a curve if you know your math, and we had a certain temperature where, okay, here are my molecules, and then there's an activation energy, there's an energy threshold, and even in this sample, some of these guys can react. So how does temperature get represented on this? Well, if that's my normal temperature, if I heat it up to a higher temperature, I will get, again, a wider distribution. It's a lower peak, but a wider distribution. And now I have more molecules, all the ones that could react before, plus these other ones. You just see that heating it up allows more molecules with more energy to get past that threshold of the activation energy, so they can react. And if we cooled it down, we use the blue one, I'll get a higher peak with a smaller distribution, and then only a couple molecules now have the ability to react, and the reaction is almost non-existent because we just took all the energy away, so none of them can get past that threshold. So this just looks at the distribution curve with that activation energy involved, pretty much like we were doing over here as well when we look at the catalysts. Catalysts actually move that activation energy. The temperature changes actually increase the energy of the molecules, and they go past that stationary threshold activation energy. And that should wrap up our kinetics big idea.